Screen share. Here it is. All right. Can you all hear me? Is the voice good?
Yes,
Is the voice good? Awesome. So we talked about having, I don't know, two balls, right? Mass M1, M2, and this is gonna have V1 initial. This is gonna have V2 initial, and when they collide, that's M1, M2. This is V2, V1 final, and this is gonna be V2 final somewhere. Now, when you talk about the kinetic energy for both of them, okay, is going to be 1/2 M1 V1 initial. Just V1 initial square plus 1/2 V2 in sorry, forget the M. M2 V2 initial square equals 1/2 M1 V1 final square plus 1/2 M2 V2 final square, which we did this, and then what we did, we multiplied everything by 2. So what we got was M1 V1 initial square plus M2 V2 initial square, which equals to M1 V1 final square plus M2 V2 final square. Now organize them where you have all the masses together. So M1 V1 initial square minus M1 V1 final square is going to equal to M2 V2 final square minus M2 V2 initial square. Factor out M1. So your M1 is going to be V1I square minus V1F square, which is going to equal to M2 factor out V2F square final minus V2 initial square. Now, using the property A minus B multiplied by A plus B, which equals to A squared plus B squared, what are you going to have?
A squared minus B squared.
Yeah, right. My bad. See, you know this. We already been through this, right? We got to that point. So be that be M1 V1 initial plus V. Yeah, that's too far away. Plus.
Scroll up a little bit, just a little bit.
See what now?
You just scroll up a little bit, please. Yes.
Yeah, so this be M1 V1 plus V1 final, V1 initial plus V1 final minus. Is going to equal to M2 V2 final minus V2 initial plus V2 initial. And you get actually V2 final minus V2 initial. Which this was our equation 2. Our first equation was the momentum that we talked about, which is, equals mv. So m1 v1 initial plus m2. Actually, let me just get a different color. Let me get blue for this one. For the momentum, which is equals to mv, what you have, I'm going to scroll down a little bit. M1 V1 initial plus M2 V2 initial equals to M1 V1 final plus M2 V2 final. That was our first equation that we had. We actually saw for the momentum. All right. So organize this also. What you're gonna have? Be M1 V1 initial minus M1 V1 final equals M2 V2 initial minus M2 V2 final. I'm sorry, V2 final minus V2 initial. Everybody with me so far? Factor out M1, V1I minus V1F, which is going to equal to V2F minus V2I, multiplied by what? M2. All right, that was still our equation 1. Actually, let me just write M2 in the front. Equals M2. That's better. So divide equation 2 by equation 1. So basically what we're saying is, let me just do a different color on this. M1 V1 initial plus V1 final times V1 initial minus V1 final is going to equal to equation 2, which is, let me just write it over here. M2 V2 plus, yeah, M2 V2 final plus V2 initial. I don't know why I'm going up like that. V2 final plus V2 initial times V2 final minus V2 initial. Now all of that divided by the first equation, which is M1 V1 initial minus V1 final is going to equal to M2 V2 final minus V2 initial. Which means your masses cancel out. And you got D1 minus F cancel out, and this is your minus cancel out. So what do you have left? So you got V1, actually let me get the same color. So your V1 initial plus your V1 final is going to equal to your V2 final plus your V2 initial. That means that your V1F is going to equal to V2F minus V2I minus your V1 initial. We're going to call that equation number 3. So you're going to plug equation 3 into.
Why are you subtracting the V2I there?
So what now?
You're subtracting the V2I?
Oh. Is that better?
Yeah, that's better.
My bad. Good, somebody's awake. All right. So we subtract this into 1. So basically, here's our first equation. Here's V1F. So what we're going to do, we're going to get V1F and we're going to put it there right over there. Well, hold up a second. Let me actually do the one on the top before modification. Actually, it's better. I'm going to put it right over there. So basically, it's going to be right over here. You see it? So let me write down the equation. So your M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. So putting it in, what you're gonna have is M1 V1I plus M2 V2I is gonna equal to M1 V2F plus V2I plus, no, not plus, it's minus, right?
Yes.
Minus V1I plus M2 V2F. Everybody good with me so far? You good, Sean?
I'm doing good. Yeah. How are you?
We're still not finished, buddy.
Oh.
You wanted the proof, didn't you?
Yes, I did want the proof. I'm like one of maybe 3 people that are awake right now, so I'm listening just fine. I'm not sure about anybody else.
Oh, everybody's listening. Trust me. When it comes
Are
to
they?
proofs, people like to do algebra more than calculus.
Mm-hmm.
You know.
I'm technically awake now.
So okay. So you're all with me right now, right? So we plug number 3 into number 1, right? Now let's make it together. So it'll be M1 V1I plus M2 V2I is going to equal to M1 V2F plus M1 V2I minus M1 V1I plus M2 V2F. Okay, so we got V2F and V2F. So this actually we can say, what is it? M1 plus M2 multiplied by V2 final plus M1 V2 initial minus M1 V1 initial. That's going to equal to M1 V1I plus M2 V2I. That means your M1 plus M2 for V2F, the one that we're trying to find, right? Because that's what we're trying to find. We're trying to find the final velocity for 1 and 2. So this is going to equal to M1 V1 initial plus M2 V2 initial plus M1 V1 initial minus M1 V2 initial. Is that right?
That looks about good, I think. I'm not exactly sure, but you got the algebra right.
Hold on. I'm taking these, putting them on the other side, right?
Yeah.
M1 V2I, this becomes negative. M1 V1I becomes positive, right?
Yes.
So that means we got 2 M1 V1. Let me just put this down actually a little bit more lower. That means 2 M1 V1I plus M2 V2I plus, or minus actually. Minus the third term, right? M1 V2I is going to equal to M1 plus M2 V2 final. Well, you got V2I, so 2M1 V1 initial plus get the V2 initial as common factor. So you get what? M2 minus M1, which equals to M1 plus M2 V2 final. That means actually the V2 final is going to equal to 2M1 V1I plus V2I for M2 minus M1 over M2 plus M1. Now, if this is, let me just go back way on top for a second. If this is standstill, it's not moving, that means V2I is going to be equal to what? to 0, right? If V2I equal to 0, that means, let me just do this in blue. V2 final is going to equal to 2M1 V1I divided by M1 plus M2. Okay? Now, well, what about V1 final? Well, we get the V2 final. Okay? And we see equation 3 is only V2, so we plug in the V2 final into, that's a long line over there. So what you're gonna have? You're gonna have V2 final is gonna equal to 2M1, not 2M1. Let me actually copy this. I don't feel well. V2F, V2I minus V1I. So equation 3 was V1 final equals V2F minus plus V2I minus V1I, right? So we're going to substitute this right over here. So that will make it V1F is going to equal to 2M1 V1I plus V2I for M2 minus M1 over M1 plus M2. You're going to add to that V2I and you're going to subtract V1 initial. That means V1F is going to equal to 2M1 V1I plus, that's a plus, V2I M2 minus M1 plus, well, we're going to all make them all under M1 plus M2. So we multiply this by the V2I by M1 plus M2, and you subtract that V1I by M1 plus M2. Whew, my hands are getting tired. Oh, what a coincidence, right? So we got V2I hold up. Yeah, V2I M1 plus minus V, and you got V2I M minus 1, M2 minus M1. Let me just get this out. Yeah, plus V2I M1 plus M2. So let me just change color again. V1F is going to equal your 2M1, and you get V2I. So 2M1 V1I, right? Plus you got V1I M1 plus M1 minus M2. Hold a second.
Isn't it a minus there?
Just a second. Let me just look at my algebra for a second. That is a long algebra equation. Hold on. Let me just make sure of my signs. So 2M1 V1I plus 2I M2 minus M1 And then you got V2 initial M1 plus M2 minus V1I M1 plus M2. All right, so let's just so you have to open it all up. Ah, that is like long. You know what? I'm gonna let you all open it up. The whole top row was supposed to be 2M1 V1I plus M2 V2I minus V2I M1 plus M1 V2I plus M2 V2I minus M1 V1I minus M2 V1I. Whew, that is long.
All over M1 plus M2.
Oh yeah, I forgot about that too. Yeah, God forbid. Or M1 plus M2. Man, we're earning our class today. So let's see what cancels out. You got M2 V2I, M2 V2I. Boom, boom. Okay.
Whoa, wait a hot second here. That's two pluses.
Oh, two pluses.
Yeah, they're added.
No, I'm sorry. My bad. Hold up. M2 V2I. Supposed to be, yeah.
Can't you cancel them though because V2I is 0?
Which one?
V2I is 0.
M2 V2I. M2. Hold up a second, dude. So this is going to equal to. Yeah, these two will be together. So V2, M2, V2I. Is that better? All right, now let's see. M1, V2I. Yeah, I got these switched. That's why. This is the two they cancel out, don't they? They cancel
Yes.
out. And then what you got? You got V1I. Yeah, you got V1I for
You can cancel out one of the M1 V1Is, I'm pretty sure. There's a 2 M1 V1I and then a negative 1 M1 V1I.
what? Cancel out what?
The first term in that entire numerator, right? It's a 2 M1, that thing, and then the second to last one.
So that equals just 1
Just 1 M1 V1I.
2M2 V2I plus V1I. Yeah, you're right. You're right. So this is just a long equation, man. Hold on a second. Let me get back to blue. So let's see what we said. We said 2 M2 V2I, and then you got V1I M2, and then V1I M, right? So that's plus M V1I, right? Minus, yeah, that's it. M2 V1I over M1 plus M2. Is that better?
Yeah, as good as it can be.
Everybody good with that? That makes it 2M2 V2I plus V1I for, that's M1. M1 minus M2 over M1 plus M2, and that's your V1 final. Whew. That is just a long, I can't believe you all made me like write that. Oh my God, that is like a long, long proof. Look how long it is.
Okay, I missed all that. Can we do it again?
You're crazy. You are
It's a
crazy.
real knee slapper.
Huh?
So
Yeah,
that's a real knee slapper.
So, but I mean, it was good to go into algebra, the detailed algebra of this. So basically, again, if your V2I is going to equal to 0, right? Let me just let me just get one more thing before I forget to write this down. Let's say when V2I is going to equal to 0, so V1F is going to equal to what? Is going to equal to, I'm sorry, M1 minus M2 over M1 plus M2 multiplied by V1I. And that's your whole proof. Happy now? We good? That is just for algebra lovers only. You know what I'm saying? This is not even calculus in there. That's algebra. And you think you know math. It is long. Actually, let me go ahead and save this as. I'm going to save it. This one 11. Formula proof. I was going to put for Sean. Okay, let's just go do this. So I'm going to actually pull this out.
Is this elastic or is it plastic? No, plastic's when they stick together, right?
Yeah.
Okay, never mind that.
No, it's one dimension. One dimension elastic collision. So let me put this up there under discussions. Man, that took like way longer than I thought it would. Okay. Let's see. There you go. It's okay. I'll put it right now on Canvas for you guys. Okay. All right. Now. All right, so let's open up a new page for chapter 10 notes. Chapter 10 is really easy. Really. I mean, it is awesome. You know. All right. So I hope you all were satisfied with all that proof. Now, supposedly, let me just do this. Your X and your Y. Ugh, that's ugly. I don't know, why doesn't it have like a coordinate system already set for drawing on there? But anyway, and here's our little proof. This is ugly too. use our little circle. Right? Now, supposedly you got, I don't know, you got something going in a circle and it's going from over here to over here. All right? So that's when we're going to define. So this is going to be basically, this one is going to be theta initial. And it ends up right over here. All right, so let me just go right over here and it's going in a velocity, v. Let me just go v like this. So that's going to be your theta initial. Your theta final, is right over here. No, I don't want blue. That means the difference between them, that's going to be your, sorry, not, I'm sorry. So this is actually, actually, you start from here. So that's your theta initial. This is actually your theta final. That means the difference between them, right over here, that's going to be your delta theta, which is called your displacement. So your angular displacement, that's what we call your angular displacement. Angular displacement. Delta theta is going to equal your final theta minus your initial theta. Now, your theta is going to be in radians. I'll explain that in just a second. Now, if you actually take the square, right? So you got something that's trying to go in a full revolution. By the way, a revolution is one full turn, one whole thing around the circle. So let's say you take this little square over here. Let me get, let me get orange. So what this was going to look like, right? You get one going in here, one going in there, but then it's like a circular path, right? So the length for this, we're going to give it a call S, which is your arc length. Now, your theta, the angle that's responsible for us to turn, is going to equal to your arc length divided by R. What's R? R is your radius. Now, this is called your reference line. I forgot to put the X. You go in from 0 to pi over 2 to pi to 3 pi over 2 back to 2 pi. So for a full revolution, your theta is going to equal to 2 pi radians, not radius, radians, which means 2 pi, that's your 360 degrees. So your 2 pi radians is going to equal to 360 degrees. Now you got an object that's going in a circle. All right? It's going in a circle with a velocity and an angular displacement. So we need to define something called your omega, which is your angular velocity. Kind of like velocity, it's angular velocity. It makes you go in a circle. Now, you know how like velocity was distance over time? So the distance on this one that you're traveling is right over here, which is your theta, your arctan divided by r. So your distance is your theta divided by the time it's taken, which is how much radians per second. Now, when something is actually going, has a velocity, that means it has a what? An acceleration. Okay, so we need to define something called your alpha, which is your angular acceleration. Which is going to equal to, kind of like the acceleration was velocity over time. This is going to be your change in angular velocity divided by your change of time, which is your omega final minus your omega initial over your t final minus your t initial. Now, notice, though, I have written a v over there. So there's a velocity perpendicular to the circle, right? To the radius. This velocity, we're going to give it a t for tangential velocity. So vt, that's your tangential or tangent velocity, which equals to your arctan divided by r, which actually this is equals to r theta, your s equals to r theta divided by t. And
what was r again? What was r again?
The radius.
And then that's just r times the thing?
Yeah. See, the radius, this is arctan over r, right? Theta.
Okay.
Arctan is over here. So the distance from here to here, that's your r, right?
Okay.
You got it?
Yeah, I got it.
Yeah, you're going in a circle, right? It's the same thing that we're doing, but everything we've been doing was in a straight line motion, right? But what if something is going in a circle, right? So your tangent velocity is your s over r, which is r theta over t. Your theta over t, again, that's going to be your omega. So that means your tangent velocity is going to equal to r omega, which makes sense. It's your angular velocity multiplied by the radius that you're going, and it's going to give you the velocity in the direction that you're going. All right? Your same thing. There's something you're going to have a tangent velocity. Means you're going to have a tangent acceleration, which is your change. Same thing. Velocity, exponential velocity over time. So it's changing tangent velocity over change of time, which is your tangent velocity final minus tangent velocity initial over time. And again, we said that Vt equals r omega, right? That means it's r omega final minus r omega initial over time, which is going to equal to r omega final minus omega initial over Tom. Not alpha, I'm sorry. AT. But we did define alpha as the change of the angular velocity over time, right? So this little thing over here, actually, let me get a different color. So let me get this color over here. So this little fella over here, that's your alpha. So that means your tangent acceleration is going to equal to R alpha.
Quick question.
Mm-hmm.
On the tangent velocity expression, does that say S over R equals R theta over T?
Yeah.
But isn't S just R theta?
Yeah, exactly. S is R theta.
Right. So where's the T coming from?
I am so sorry. I am so sorry. So sorry. Dude, it's velocity, distance over time. The T. Is that better?
Yes, thank you.
Yeah, because if it was R, we cancel out and we just have like theta. That's it. Yeah, you're right. My bad. I've had enough algebra for it's like a lot of algebra today. I'm seeing all kind of like, woof. All right. So that means your tangent velocity is R alpha, which is in radians per second squared. See, your velocity is going to be in radians per second. Okay? So let me just check something. All right, so let's see over here. So in the simplest kind of rotation points on a rigid object move on a circle path around, points on a rigid object move in a circle path around an axis of rotation. We actually going to be talking about a little bit about ice skate figures and like the relationship that you have with the radius and the velocity in just a second. So the angle through which the object rotates is called your angular displacement, which is your final theta minus your initial theta. So when a rigid body rotates about a fixed axis, the angular displacement is the angle swept out by the line passing through any point on the body and intersecting the axis of rotation perpendicularly. Now, the unit for it is your radians, right? So you go basically in radians for your angular displacement. So let me just move this. So basically your angle, your theta in radians is going to be your arc length, which is this right over here, divided by your radius, r. For a full revolution, it's 360 degrees, so it's 2 pi radians. So 2 pi radians is 360 degrees. So here's a question for you guys. Satellites are put into an orbit whose radius is 4.23 times 10 to the 7th meter. If the angle of separation of the two satellites is 2 degrees, find the arc length that separate them. All right, let's go ahead and I'll go ahead and solve it. So your radius is how much we say? 4.23 times 10 to the 7th, you get 2 degrees, right? So 4.23 times 10 to the 7th meter, and your theta is 2 degrees, right? Which is, you actually convert it so it's 2 degrees multiplied by 2 pi radians per degree. These go away. So what you have, 4 pi radians, which is oh, sorry, 2 pi over 360 degrees. 2 pi radians is 360 degrees. So you get 4 pi over 360. Somebody plug that in. What you get? You're looking for S. I got 0.0349 radians. I don't know if that's what y'all got.
I
That
got
means-
that.
Yeah, that means your theta equals, well, let me just say this. That means S equals theta R. That means your S that we're looking for, your arc length, is 4.23 times 10 to the 7th multiplied by your 0.0349, and we should get 0.03 times the 6, 0.14 times 10 to the 7, right? Yeah, 0.14 times 10 to the 7th meter, right? Which is what, 14 times 1.4 times 10 to the 6 meters. Is that what you all got?
Yep.
Let's look. So your radiance, your theta is going to be your arc length divided by radiance is divided by R. So it's 2 pi divided by 360 multiplied by 2, so you get 0.0349 radians. So you multiply it, yeah, we get 1.48 times 10 to the 6 meters, which is 920 miles. Okay, so how do we describe the rate at which angular displacement is changing? That's when we introduce your angular velocity. So your angular velocity is your angular displacement divided by your time. Your units for the angular velocity is radians per second, meters per second, but you're dealing with your velocity radians per second, meters per second, you're dealing with angular, so it's radians per second, which is basically is your limit from delta t to 0, delta theta over delta t. Now, changing angular velocity means there's an angular acceleration that you have. The angular acceleration is your change in angular velocity divided by your time, which is going to be in radians per second squared. So here's a question for you guys. Seen from the front of the engine, the fan blades rotating at an angular speed of minus 110 radius per second. As the plane takes off, the angular velocity of the blade reaches minus 330 radians per second at 14 seconds. Find the angular acceleration. So we got, what do you got? Did we skip something? No, we didn't. Okay. So that means your angular I is minus 110 and your final is minus 330, right? It's going opposite. That's why, by the way, it's negative if you're noticing. But so your omega I, that's example 4, is going to be your minus 110 radius per second, and your final is minus 330 radius per second. And what you got, 14 seconds, and you're looking for alpha, which alpha is the omega over dt, which is minus 330 minus 110 divided by 14.
Minus negative 110?
Negative 110. Oh, somebody's awake. So what you got? Minus and minus is positive. 330 minus 110, what's that? 230, right? 220 minus divided by 14. So
Like 15.7 and some change, right?
yeah, minus 15.7, right? Meters per second, which is, I think is 16 in that question. Yeah, minus 16, that's correct. And again, it's going counterclockwise, right? So yeah, minus, I'll just write it minus 60 meters per second. Not meters per second. Why do you tell me meters per second, man? You didn't catch that one? Radiant.
Sorry.
Oh, yeah, you called out the algebra. Oh, there's a negative over there, but you didn't catch the units.
Hey, it's per second squared though.
Now you're awake. Right? So remember when we had our kinetic equations, right? So we had your V final equals your V initial plus A T. Your distance equals 1/2 V naught plus VF multiplied by T. We had VF square equals V naught square plus 2AD. And your D equals V naught T plus AT square over 2. Remember those 4 beautiful equations that we had? Well, that's for linear. Now for angular, you're just going to replace the velocity with omega, okay, and the acceleration with alpha. So this one be omega F equals omega initial plus alpha T. Theta is going to equal to 1/2, that's your distance theta, 1/2 omega initial plus omega final multiplied by T. Your omega final square is going to equal to omega initial square plus...
Wait a second. It's a theta up there, or is it like an S?
No, theta, your displacement.
It's not S, not angular, whatever displacement. Or the angular displacement is theta, but not like the arc length displacement. It's a different one.
Yeah, the angular displacement, exactly, because that's actually what dictates how fast you go, where you go.
Okay.
Okay? Your arc length is that one, the one we just did. Now, this is 2 alpha theta, and then the last one, your distance theta equals omega naught T plus alpha T squared over 2. And yeah, you were correct. I was about to write that down. So your V was omega, your A is alpha, and your distance, that's your theta. So, that's the 5 kinematic variables that we have, that we do, and changing them in there, you get your angular displacement, right? Your angular velocity and your angular acceleration. Now your angular displacement again equals r theta. S equals r theta, right? Now, it's right over here to have it for y'all. So let's do this example real fast, right? You got a blade whirling at an angular velocity of 375 radius per second, and it got a displacement of 44 radius. Okay, so let me just write this down. So omega naught equals how much we said? 375 meters per second. And then we got a theta of 44 radians. And your alpha is 1740. 1740 radians per second squared. and you want to find the final angular velocity. Well, same thing. You're going to go inside over here to our equation. So what do you have? You have omega naught, theta, and alpha. The only thing you don't have is t for Tom, right? So that means you don't have t. Eliminate this one. You don't have t, you can eliminate this one. You don't have t, you can eliminate this one. So this is one you have. Omega final square equals omega naught squared plus 2 alpha omega. So omega final square equals omega naught squared plus 2 alpha theta. That means your final angular velocity is going to equal the square root of omega naught squared plus 2 alpha theta, which is 375 squared plus 2 multiplied by 1740 multiply by theta, which is what, 44? What do you get? 5. So 1740 times 2, that's what, 3480. 3480 multiply that by 44. That's 3034 4 times. That's 140, and then 80. And 80 is 160. And 160, 320, what's that? 140, 320. The 336. Square root. Square root of that be 5 and change. I'll give up. 5. Somebody plug it in. What do you got?
541.98.
Oh man, I was close, damn it. Wow. I still got it. Heck yeah. Wait, who needs a calculator? Let's see. Yeah, 542. So we are good on that. Now, we talked about something having tangential velocity, right? But what is a tangential velocity, actually? You know, and that's what we just talked about. Your tangential velocity is your S over T, which your arc length equals R theta, okay, divided by T. Now, here's the difference. Whoever asked me that question, you need the velocity on that path over here. That's what the tangential velocity is, perpendicular to the displacement. You see that? The radius. Okay, so it equals R theta over T, which is omega. Your angular velocity is theta over T, so it's R omega. Same thing with your tangential acceleration, right? It's your velocity over time, which is tangential velocity over time, which means it's R omega final minus omega initial divided by time, so it's R alpha. So let's say a helicopter blade has an angular speed of 65 revolutions per second and an angular acceleration of 1.3 revolutions per second squared. For point 1 on the blade, find the magnitude of the tangential speed and then find the acceleration speed. Okay. So 6.5 revolutions per second. That's your speed, angular speed, right? So your omega, example 6, 6.5 revolutions per second. But we want to change it to radians per second. So it's 2 pi radians per revolution, 1 revolution, which is 360 degrees. These go away. So this is going to equal to 40.2 pi, 40.8 radians per second. Now let me just look over here. Your alpha is 1.3 revolutions per second square. Same thing, your alpha is 1.3 revolutions per second square. Again, you can multiply that by 2 pi radians per revolution. Again, revolutions cancel out. So this is going to equal to 2.6 pi radians per second square, which is 3.14. So that's 6.14 plus you get a 0.6. So 8.1, I would call it 0.17 radians per second square. That means your tangent velocity is going to equal to what? To r omega, which is, what's r? Do we have r? Yeah, we need 0.1, so it's 3. You see that? Let me just write this down. Your r is 3 meters. So this is going to be 3 multiplied by 40.8, which is 122 meters per second. Your tangent acceleration is your r alpha, which is 3 multiplied by your 8.17 that we found, which is 24.5 meters per second square. Now, that be good? Now, we also talked about, I don't know, balls and stuff moving in, like a billiard table or whatever, that has a mass of, object has a mass of m and velocity of v. Well, before I go there, let me just do this first. Now, I'm going to define also something called Ft. That's your tangential force. Tangent force. Yeah, now your tangential force is going to equal, now what's the force going to equal to? Your mass times acceleration. So your tangential force is going to be mass multiplied by AT, which is going to be R alpha, which alpha is your angular acceleration. Now, usually, when you have a force multiplied by your radius, you're going to have a torque. This is your radius. So that means that your tangential force is going to equal to the torque divided by the radius that you're going on. Right? So your torque really is your mass multiplied by, instead of A, R alpha multiplied by R. So it's M squared R alpha.
It's R squared, right?
R squared. I'm going to finish this chapter today if it kills me. Anyway, so your mr squared, that's what we call I, your moment of inertia. That means your sigma torque is going to equal to your summation of mr squared multiplied by alpha, which is again your I alpha. And your I, again, is your summation of all the masses multiplied by your radius squared. So let's say, for instance, you have a pulley with a rope. So this is your rope.
Can you go back to that last slide really quick and scroll down a little bit? Thank you.
Then when you're done.
All right, I'm good.
Okay. Now, that's your radius R, right? And you're going with a pulley, so it's going this way. You're pulling the rope, so your theta is going that way. You know, you got a force going in this way, right? That's a pulley. That means your work, which is your force multiplied by your distance, right? Which is in this case, your F multiplied by your S, which your S is going to be R theta. That means your work is going to equal to FR theta. But your FR, we said that was your torque. So this is going to equal to your torque multiplied by theta. So let me get a different color. So your work is your torque multiplied by theta. Now again, theta must be in radians. And your work has to be in what? In joules. Now, if it's moving, so it's going to have a kinetic energy, right? The pulley is moving. That means it's going to be 1/2 m, and is a tangent velocity square. And again, your tangent velocity, Vt, is r omega, which is r against the radius. Omega, that's your angular velocity. That means your kinetic energy is going to equal to summation of 1/2 m r square omega square, which equals to 1/2 summation of mr square omega square. Again, that's your I, so it's 1/2 I omega square. So your kinetic energy equals 1/2 multiplied by inertia, by your inertia multiplied by your angular velocity. And this is your rotational kinetic energy of a rigid rotating object.
Is that W or omega
Which one?
in the kinetic energy equation?
Omega. So, 1 second. So if you got a mass, ball of mass m going at, oh no, I don't want that. Going at v, velocity, right? You're also going to have your momentum, which is your mv. Now, we talked about momentum, right? How much momentum something has? Okay, so the more momentum, the harder for it to stop. Now, to change momentum, you have to apply a force for an amount of time. So you change your momentum, you're going to have to apply a force in an amount of time. Right? So, this is your change in momentum. And we call this your force multiplied by, I forgot the T. What we call this, guys? Your J, which is your impulse. So if you have, this mass that we have and pivot it on a nail with a string, right, it's going to go, if we do a torque on it, this side is going to go that way. And this is your R, right? So this is your starting point. Now it's going to have an angular momentum. Now, your angular momentum you're going to give it the letter L. And the reason you're taking the letter L because they ran out of alphabets to give to variables, so they gave it the letter L. That's going to equal to your mass multiplied by your tangent velocity multiplied by your radius. Okay? And again, your tangent velocity is your velocity perpendicular to the radius. So when you have no torque, that means you have no angular momentum. You see your angular momentum is mvtr. If your radius, something like this, if your radius is small, you have a velocity. If your radius gets bigger, guess what happens to the velocity? It goes down. So, and I'm almost done, guys. Just give me a second. I might just go 5 minutes over. But so you get your radius, and you get your tangent velocity, and you get your omega. When your radius goes up, that means your velocity goes down, which means your angular velocity goes down. If your radius goes down, that means your angular velocity goes up, which means your angular velocity goes up. So your angular momentum is going to equal to m. Your Vt is your omega r multiplied by r, which is m omega square r, omega r square. And again, your omega r, that's your I, so that makes it your angular momentum L is going to equal to I omega. Now the units for this one is going to be kilograms meter squared per second. Hold up a second. So let me just go over this one. Already been through all this. So we define the tangential acceleration. We define also the acceleration, radial acceleration, which is v squared omega squared multiplied by r. And we just did the proof for your kinetic energy, which is 1/2 I omega squared. Let me just write this down. Now, your kinetic energy, again, is 1/2 I omega squared. So for rotational. And that should be it for chapter 10. Yeah, that should be it for chapter 10.